Last class, we had a veritable yap sesh, me chatting about all the fun stuff that shows up with intermolecular forces. We talked about ways that things change from solids to liquids, melting, liquids to solids, freezing, solids to gases, sublimation, like the little ice crystals that show up randomly in your freezer, and then you've got dry food for some reason in your freezer. We also talked about boiling, we talked about condensing, we talked about, vapor pressure. Remember that we talked about vapor pressure. You can increase vapor pressure with increasing temperature, decreasing strength of intermolecular forces. Unlike rate of evaporation, surface area does not affect vapor pressure. I'm missing the word area in there. Surface area does not affect vapor pressure. And then we capped off talking about boiling. Boiling is a phase change, meaning that we're changing between two states of matter. When we're boiling, we're changing between liquid, our middlest energy state, and gas, our highest energy state. Any time that we're doing a phase change, our temperature is locked in. And so we also had the same thing. If you remember back, we were talking about ice water. Ice water has ice, solid, and water, the liquid form, together. And when those two things are together, that temperature is locked in at the freezing point. Same thing with boiling. If you've got the gas and the liquid, we're locked in at the boiling point, which is why you can cook your pasta with just setting a timer. Now on to energy. What happens when we melt? What happens when we freeze? What happens when we evaporate? What happens when we condense? What's the energy exchange that is going on when we are doing these things? You probably know that adding ice to a drink cools it because melting is endothermic. What does endothermic mean? It takes in or absorbs heat. You have to put in heat to the ice cube in order for it to melt. The ice is in the solid state. This is another of my favorite graphs. We've got energy on our y-axis. There's no x-axis. We've just got our solid. That's our lowest energy state. Our liquid is a higher energy state. If you add a bunch of heat to something that's a solid, if you add enough heat, it'll eventually get to a liquid. If you add more energy into the liquid, assuming it doesn't decompose, it'll turn into the gas. Gas is our highest energy state. So in order for you to take something from a solid to a liquid, you have to add energy in it. It has to gain energy to move up on this graph, this little one-axis graph. And so that's why it's endothermic. It absorbs heat. It turns from the solid into a liquid. The reason, if we think about what's going on at the atomic, the molecular level, the reason that it's endothermic is, remember that in our solid state, everything is locked in its place. We're thinking of people at a movie theater. We're thinking of people in the classroom. You're stuck in your spot. You can kind of move around. You can vibrate in your place. When we go to a liquid, you can move past your neighbors. They're no longer stuck in their places. And so we're partially overcoming those attractions between their neighbors. We're no longer locked in our position. We can kind of swap spots with our neighbors. It's more like the very front section at a concert, like if you went and saw William Eyelash, for example. Can move past and around neighboring molecules. That's a very specific reference to Rainn Wilson meeting Billie Eilish, by the way. As we all knew. Freezing, on the other hand, when we're freezing something, we're going from a liquid, our middlest state, to a solid, our lowest energy state. In order for us to go from a middle energy state to a low energy state, that energy has to go somewhere. We can't simply just poof, get rid of it. And so that energy has to be released. And so this is going to trip some people up. Freezing is exothermic. It feels like this is not correct. we normally don't think of like, oh, you're losing heat to become a solid. This one trips people up all the time. So I'm pointing out that this is going to trip you up. But if we think about it, this is the way it has to be. If we absorbed energy, that would just take us higher and higher in terms of our energy, right? That would move us further up if we were a liquid, and we gained energy if we were endothermic. We would go to the gas state. You actually have to release energy to become the solid. And so the way that your freezer works, how it turns water into ice, is your water is just hanging out, and your freezer, through the magic of physics, pumps heat out of the freezer compartment. It removes the heat from the freezer compartment, and then the water that's in there loses heat to the compartments that it's in. Let's demonstrate again why I'm not an art major. All right, we've got our little ice tray there. We've got our water in the ice tray. We've got our little magic box, a compressor, and a refrigeration coil. So this removes heat. And now the surroundings, our freezer compartment, is colder because the heat's getting pumped out. And so what happens, our water emits bacon. I'm just kidding, it's heat released. So our water loses heat to the environment, just the surrounding air, and that causes it to cool down. Eventually it cools down enough that it can freeze. And our magic box and compression coil remove the heat. So freezing is exothermic because the opposite process, melting, is endothermic. The quantity that we use to describe the amount of heat that's transferred, the heat exchange that goes on when we melt or freeze something, is the heat of fusion. We shorten heat to delta H, and then fusion gets shortened down to FUS. Heat, usually in joules or kilojoules. This is the quantity Q when we see it in stuff like Q equals MC delta T or MCAT. So this delta H sub FUS is heat to melt a solid, specifically 1 mole. So if we see it in just a melting process, we're going from a solid to a liquid. To go from a solid, which is low energy, to a liquid, which is higher energy, you have to put energy in. So this gets a positive sign. That positive sign will often be omitted. So if there's no positive sign, you just have to know by the absence of the negative sign that it's positive value. So energy is going in. And this is heat that's going into our solid to turn it into a liquid. There's also this secret per mole bit that is almost always excluded. It's always there. We always are talking about this in terms of per mole, but it's usually omitted. So that's our heat of fusion. There's also the same amount of heat involved when we freeze water. So we have the same amount, the same number, but negative if we are going the opposite direction. So now we are going from a liquid to a solid, so we're freezing our water. As we talked about previously, that's exothermic. Heat is being emitted or released so that our water can settle down and get into its solid state. So it's a negative value. It's the same number because it's the same process, just it's the opposite process, so it's a negative sign. And again, there's this secret per mole that's almost always left off that you need to know is there. It's not per gram, it's not per kilogram, it's not per liter, per mole. And again, this delta H is negative because freezing is exothermic, which is not intuitive. It feels wrong, but it's correct. Energy is lost to cause the water to freeze. Our heat of fusion, again, that's delta H with a little sub FUS for fusion. We can use to calculate the amount of heat, energy, joules or kilojoules typically, or calories. You can do it whenever you want. But we can calculate an amount of heat required to melt a given amount of solid or freeze a given amount of liquid, because it works both ways, they're just opposites. So we're going to use this heat of fusion, our delta H, as a conversion factor between moles of solid and the amount of heat required to melt them. And let's see what that looks like. We want to calculate the amount of heat. So we're finding amount of heat absorbed when a 25.4 gram ice cube melts. The heat of fusion for water at 0 degrees Celsius is 6.02 kilojoules per mole. This time, we've been a little nice with the problem. We haven't left off the per mole part because we've written the whole thing out. Okay, so we are looking for an amount of heat. What's a unit of heat? Huh? There's one on the screen. Can somebody please identify the unit of heat? It's not Celsius. Celsius is a unit of temperature. Kilojoules. We want kilojoules as our answer. Really, we could use any value of heat, but kilojoules is the easiest, so we're going to end in kilojoules. And the place that we are going to start is actually with 25.4 grams. General rule of thumb, if you've got something with simple units, start with the simple units. So this 6.02 kilojoules per mole, this is a conversion factor. Anything that's got multiple units usually, in my mind, usually means that it's a conversion factor. So starting with grams, we want to get to kilojoules. We've got this thing that's got kilojoules per mole. What would we need to use this conversion factor? What units would we need to get kilojoules out? Moles. So this is grams of water, H2O, ice cube, water, not the wrapper. And so we need what to get to moles of H2O? Molar mass. So we need a molar mass for water. It's 18.015 grams per mole. We'll add the H2O labels on there and a 1 just to be completely robust. Okay, so we do that. Our grams H2O cancel. Now we've got units of moles of H2O. So we do 25.4 divided by 18.015. And we get 1.409 ... because there's other stuff, moles H2O. Now we can apply our conversion factor, our 6.02 kilojoules per mole. It's kilojoules on top, moles on the bottom. We have moles on the top. We want kilojoules out. So we want the kilojoules part, the 6.02 part, up here on the top. and that means that the per mole part gets sent to the bottom. And it's for water, so we can tag on the H2O if we really care about getting rid of that H2O part. So moles H2O cancel. We're multiplying by 6.02 from our previous answer. We get out 8.49 after we round kilojoules. So that's the energy that you would have to put in to melt 25.4 grams of ice. Questions about that? Great. There's another set of processes, evaporation. Evaporation is going from what phase to what phase? What state are we going from and what state are we going to? It is liquid to gas. Right, evaporation is going from a liquid to a gas. Evaporation is endothermic. Gas is a higher energy state than a liquid. On our little, this graph that I like, temperature also works instead of energy. So evaporation is endothermic. We're going from a liquid to a gas. You have to put energy in to get it to evaporate. And this is because energy is required to break the molecules away from the liquid. So when we're going from a liquid, in a liquid, we're in contact with our neighbors. Again, this is us at the front of the concert. And then when we go to the gas phase, there's empty space between us. So we need to overcome the barriers between the people, the intermolecular forces that are keeping our molecules, our particles together. We have to completely overcome those interactions to completely separate our particles and to become a gas. And that's a lot of energy, by the way. So completely separate from neighboring particles. Instead of just being able to move past them like when we were melting. And our bodies use the endothermic nature of evaporation for cooling. So more practical applications of what we're learning. As sweat evaporates, it absorbs heat from our bodies. The sweat is not a boiling point. Even if it was, it would still be taking energy to get it to evaporate. So our bodies put some heat into that water. The water evaporates, especially amplified with a cooling breeze. When it evaporates, it takes away a lot of energy, and that causes us to cool down. So that's why sweating is great. You've probably heard the phrase, since you're here, but it's a dry heat. Right? We've probably heard that. And the reason that that's important is because high humidity slows down evaporation. And when you slow down evaporation, you prevent cooling. And so instead of your sweat evaporating, it just kind of sticks on you and you're just wet and miserable from your sweat. That's when you're in a high humidity situation. We have but it's a dry heat, low relative humidity. Our sweat evaporates quite easily, and so even 115 degrees, if you're in the shade, is somewhat bearable. Like you can live there. If you were in 115 degrees Fahrenheit and it was 90% humidity, you die. So, kind of a big difference there. Even 90 degrees Fahrenheit at 90% humidity is unbearably hot. So when the air already contains high amounts of water vapor, sweat does not evaporate as easily, making our cooling system less efficient. High amounts of water vapor meaning high percent relative humidity. Like in the South. But it's a dry heat. What we actually mean by that is your sweat evaporates. You can get out of the shower and you're not immediately sweaty again and feel like you need to take another shower. If you've never traveled to somewhere with high relative humidity, give it a try. It's miserable. So that's evaporation. Condensation, the opposite process. Condensation is going from a gas to a liquid. Condensation is exothermic. Energy is released because we're going from gas to a liquid. I'm drawing the graph again. Let's draw it with temperature instead. Gas, liquid. We're going from a gas to a liquid. You have to lose energy to turn into a liquid. No longer have enough energy that you can break away from your neighbors. You get stuck, you get trapped because of the intermolecular forces. So some effects of this. As steam, if you've ever gotten in contact with really hot steam, when steam condenses on your skin, it releases heat, and it releases a lot of heat. And that is what causes the severe burns that you can get from steam. Also, steam can be hotter than 100 degrees Celsius. So unlike just coming into contact with boiling hot water briefly, the steam is going to hit you and cool down, and then it's also going to condense, and it's going to dump way more heat when it does so. The exothermic nature of condensation is also a reason that overnight temperatures tend to not get as low when humidity is high. When you've got high relative humidity, as the temperature starts to come down, there's an inverse relationship between relative humidity and temperature. So when temperature goes down, relative humidity goes up. When relative humidity hits 100%, stuff starts to condense out, and that's why we get dew in the morning, where there's a dew point. That's also why we get fog, like our thick Thule fog that we get around here. So as temperature drops, water condensing releases heat, and that heat helps prevent the temperature from dropping further. So when it's relatively dry as well, our temperature can also fluctuate a lot more because there's less water in the air. Another place that this shows up is if you're drinking water from an uninsulated water source, if you can imagine that. You're not drinking it from an Awala or a Stanley or a Yeti, and you get the water condensing on the side of your glass because you've got ice water that you're drinking and it's relatively warm outside. That water that condenses, when that water condenses, that's actually adding a lot of heat to your glass. If you wipe it away, you're making room for more water to condense. That water actually acts as a little bit of an insulator. So unless you're concerned about getting your coffee table wet or something, if you just leave it there, it'll stay cool longer. Okay, back to stuff that's important. Heat of vaporization. So heat is the delta H part, and then vaporization, like evaporation, just a different word for it, gets shortened down to VAP. And just like delta H FUS, the heat of fusion, this is the amount of heat required instead of fusing, melting, freezing, we are vaporizing. So we're vaporizing, and this is again for 1 mole of liquid. When we're doing vaporization, we're going from a liquid to a gas. That's an endothermic process. The heat of vaporization of water at its normal boiling point is 40.7. So this is going from a liquid to a gas. It's positive because it's endothermic. The water in the liquid state is gaining energy, and it's 40.7 kilojoules per mole. Does anyone remember what our delta H of fusion was? Roughly. Yeah, it was like 6. So about 6 kilojoules. This is like 40.7 kilojoules. So this is like 6 2/3 times more energy to completely separate versus just being able to travel past your neighbor in the melting process. So this is way more energy. A fun thought experiment that I've thought about is what if you just magically swapped these values so that delta H of fusion was 40.7 and the delta H of vaporization was 6.02, and what would that be like? So that's a fun thought experiment you can engage in if you're feeling quirky. Again, this delta H is positive because vaporization is endothermic. You have to add energy in to get your water to boil to evaporate. That's why cooling works. That's why sweating to cool down works. There's the opposite process, which uses the same number for condensing. So it's still 40.7 kilojoules. It's still per mole. This time, though, it's negative. Heat lost or released, exothermic, instead of a positive value. Delta H values are things that you will be given on exams. You do not need to memorize them. I will give them to you. If you need them. If I, for some reason, don't give you a delta H value and you think you need it, it's possible that I made an oopsie. Just ask, and we'll look it up. Okay, so we can use heat of vaporization to calculate the amount of heat required to vaporize a given amount of liquid. It's awfully similar to our heat of fusion that we looked at a couple slides ago. Heat of vaporization is a conversion factor between moles and amount of heat required to vaporize it. Now that we've already done one of these, basically, I'm going to give you one to do. So please calculate the amount of heat in kilojoules required to vaporize 1.75 kilograms of water at its boiling point. The heat of vaporization is 40.7 kilojoules per mole. All right, so this follows the same format as our heat of fusion calculation that we did earlier. We're starting with the amount of water. The at its boiling point here is just letting us know that we can use this 40.7 kilojoules per mole. It's another one of those, we're just preventing somebody doing an actually. And we are finding the amount of heat. This time it did ask for it in kilojoules. That doesn't really affect what we do. So starting with our kilograms of water, because heat of vaporization has the kilojoules in it, but it also has moles, that tells us that we need to multiply, since it's kilojoules over moles, we need to multiply by moles, this number, by moles, to get rid of the moles, and then that'll unlock the kilojoules that we want. So we have to get to moles. And to get to moles, we need to use the mass of water. So 1.75 kilograms of water. Kilograms are bigger than grams, so we're going to have more grams. 1.75 kilograms, 1 kilogram is 1,000 grams. So this turns into 1,750 grams of H2O. To get from grams to moles, we need to use our molar mass. Just going to reposition everything here. So we need our molar mass, which is 18.015 grams per mole. So that'll give us the moles that we were looking for, which is a big number, 97.1 ... moles, which is a lot of water for what we usually do. We take those moles, we multiply it by our heat of vaporization. The moles cancel, and we round for 3 significant figures to get 3.95 times 10 to the 3 kilojoules. That would look something like 3,950 in standard notation. Questions about any of those parts? Things. Cool. Here's a bonus that I don't want to do, so we're going to skip it. If you'd like to know how to do this bonus, though, I don't think Logan has seen it before, so he'll have fun solving it, because it is a fun problem. And when I say it's a fun problem, that usually means that it's not fun for you. But it is fun. Some of you might find it fun. You can watch. I've got solutions for that in previous videos. All right. We can also do this fun thing where we come up with a heating curve. So this is a graph, as you may have guessed by the shape. In our graph, we've got time on the x-axis. So what we're doing here is we've got water, starting off with some phase of water, and we are putting heat in. So think of it like we've got a big pot on the stove, or like a pressure cooker on the stove, and we've got heat putting in, we've got the burner turned on. So over time we're adding more heat in. On the y-axis we've got our temperature. So we can see that over time our temperature is going up. What states of matter are we going to have in each of these line segments? So our first line segment, this A to B, what phases of matter are we going to have in this AB section? What's the freezing point of water? 0 degrees Celsius. So at 0 degrees Celsius, that's when our water freezes. If we're below 0 degrees Celsius, we would expect that it's all solid. We would expect that it's all ice. So this AB section, we just have ice, our solid phase. And then we hit this weird plateau. We've talked about we're adding heat in as we go left to right. Right, we're adding heat in as we move left to right. Why do we have this flat line where our temperature isn't changing at all? We're adding heat in, but our temperature isn't changing. What's happening there? What's happening there? We're melting ice. So we've had ice, some started to melt, and now we've got ice and water at the same time. And since we have ice and water at the same time, our temperature is locked in. So we've got solid and liquid. Our temperature does not start to change until what happens here at C. Any ideas? When we had the solid and the liquid, our temperature would not change. If our temperature started to change, what does that mean about what we have? We have no more ice. We have entered the unruly, unpredictable water temperature phase. So for C to D, this section, we just have liquid water. We're heating liquid water. When we get to D and to E, this is when we are vaporizing water. So we've got liquid and gas. So this very long section, it's much longer than the melting ice section because the delta H vap is much higher than the delta H FUS. So there's a lot more energy required to get the water to boil. We're locked in because we've got liquid and gas. We've got two states at the same time. And then here from E to F, we're above 100 degrees Celsius. We are just gas or water vapor at this point. All right. Questions about any of the things that are happening on this graph? Part of the reason that I show you this is because there are some calculation questions that we can do that involve thinking about these different line segments and what's happening with our state changes for water. So like, for example, we have the tools. We might not like that we have the tools, but we do have the tools that I could tell you, hey, you're starting with a certain amount of solid ice, solid water, and then you put in a certain amount of heat, what phase does it end up in? Which would be a crazy question. You could also calculate, you start off with some ice, we turn it into steam at a certain temperature, how much energy was put in? And it's a lot of steps, it's a long calculation. It's not complicated, it's just a lot of steps. Here it is. This is actually a shorter version. So in this example, if a 50-gram ice cube, 50-gram ice cube at 0 degrees Celsius is added to 500 milliliters of tea at 20 degrees Celsius, so we've got ice, we've got tea. What is the temperature of the tea when the ice cube has just finished melting? So as soon as the ice is gone, what's the temperature of the tea? We're going to make some assumptions. No heat is transferred to or from the surroundings. Very nice. We're going to assume that the density of water and our iced tea is 1 gram per milliliter. And we've got some C values. C water, C ice, and our delta H fusion for ice. Okay, what is going on? You might be thinking to yourself, we've got a lot of stuff here. So we've got drawing time. We've got a glass, and it's got tea in it. So I'm going to make it green because it's green tea. We've also got ice. It says that we've just got a 50-gram ice cube, but let's just say it's 50 grams of ice. All right, so we've got our ice in our cup of tea. And then, whoa, sneak peek. Later, we've got a state where we just have the tea. So we're melting the ice, and we want to know, as soon as the ice is done melting, what's the temperature of our tea? What's happening when our ice is melting? What energy-wise, what's happening when ice melts? It's endothermic. Our ice is absorbing energy. So ice absorbs energy to melt. Where does it get that energy from? It gets the energy from the tea. I also get energy from tea. So in lab, if you've got some juicy stories, please share. So the energy is from the tea, which means the tea is losing energy. Q is what we use to specify heat. So the negative Q of the tea, this is heat lost by the tea, is equal to the Q of the ice. This is just saying that this is equal to the heat gained by the ice. So ice absorbs energy to melt. The energy is from the T. Mathematically, we represent that this way. So the amount of heat that our ice gained is the opposite of the heat that was lost by the T. Can we calculate the heat that was absorbed by the ice? Yes, we can. So this is where we're using, not that, this, heat of fusion. We're doing a heat of fusion question. So we want to know how much energy went into the ice. Once we figure out how much energy went into the ice, we know how much energy was lost by the water. And then we can do Q equals mc delta T. So this problem in particular, challenging because we've got basically two parts. You have to identify the two parts and how they link together. So our first part is how much energy gained by the ice. We started with 50 grams of ice. Ice is just H2O. We've used this molar mass before. 18.015 grams per mole. It's 1 oxygen plus 2 hydrogens. So this will tell us how many moles of water we have. And then we can use our delta H of fusion for ice to get the kilojoules. So multiply 6.02 kilojoules per mole. And this is the amount of energy that was gained, or the amount of heat that was gained by our ice. 16.7 ... kilojoules. All of that energy came from our T, came from the liquid. So that's all from the water that caused the T to cool down. Do I have questions so far? All right, so this is where we jump into the second part. Energy lost by water. Since the water is losing energy, that causes it to cool down. We're using Q equals mc delta T, where delta T is the final temperature minus the initial temperature. We haven't used Q equals mc delta T in a while. It'll probably show up on the next exam. It'll definitely show up on the final. Our Q value is the 16.7 ... kilojoules. So when we're using this, because our C value has joules, we want this to actually be in joules. So 16,708 ... joules. So negative 16,708 ... joules, because the Q of the T is the opposite of the Q of the ice. So it's just a negative sign. We're losing this much heat. Equals our mass, the 500 milliliters. Our density is 1 gram per milliliter. This lets us swap out, or swap in grams for milliliters. So 500 grams of water, and our C value 4.184 joules over grams degrees Celsius, and delta T. Delta T contains our final temperature, which is what we're looking for. So I'm going to rearrange this so that delta T is equal to some value. And I'm not going to talk through the whole thing. Maybe I will. So we're going to take our joules, we're going to divide it by 500. We're also going to divide it by the C value, 4.184. And we get negative 7.986 dot, dot, dot. This is going to have units of degrees Celsius equals our delta T, and delta T is TF minus TI. So this is equal to our final temperature minus our initial temperature, which was 20 degrees Celsius. So our last step, we add 20 to both sides. And TF is, if I do it correctly, 12.0 degrees Celsius. That's the theoretical temperature of our T. Questions about any of the parts of that and how we put it together? If you'd like to do more questions like this, Logan can come up with questions like this. He'll just change the numbers. You could also do a more complicated version, since in our calorimetry lab, we did like, hey, what would the final temperature of the two water mixtures be? You remember we calculated that? And I was like, that's a lot for this class. We could also do that, since our ice just melted, so our ice is going to be at 0 degrees Celsius. We could also calculate what the final temperature of the water mixture would be. I'm not going to give you that on an exam because that's evil. It's mean, at least. It's maybe not evil. I think it's morally wrong. Okay, so that's energetics. Now, I've given you a lot of problems, so now I'm going to give you some solutions. Solutions are homogeneous mixtures. Who remembers what a homogeneous mixture is? What's homo mean? Same. So a homogeneous mixture means we've got the same consistency throughout. Same consistency. Things like watermelon Celsius, just to name one particular thing. Any other beverages, most other beverages are also going to be homogeneous mixtures. It's got the same smooth consistency throughout, everything's evenly distributed. Solutions are really common. Most of the liquids, most of the gases that we encounter, like the air we're breathing, the water that we drink, are solutions. The ocean is a solution of salt and other solids that are dissolved in water. Blood plasma in our veins has blood cells removed from it because it's just the plasma, but there's solids and some gases that are dissolved in the water that runs through our bodies. There are many common types of solutions. Here's, I think, all of the types of solutions, or most of the types of solutions. We haven't learned what solvent phase or solute phase are. It's just one of the two components. So solvent's one component, solute's another component. You can have gases mixed in gases. You can have gases and liquids. You can have liquids and liquids. You can have solids and liquids. You can have solids and gases, solids and liquids, and solids and solids. And we're not going to talk about most of those, but they exist. Those solutions are possible. So solids and solids, things like steel alloys, we're not going to talk about most of those. Typically what we are talking about when we're talking about solutions and homogeneous mixtures, we're talking about liquids in liquids or solids in liquids. More often than not, it's solids in liquids. Our two components, our minimum of two components, are the solvent and the solute. The solvent is the majority component. The solute is the minority component. So the solvent is the one that we have more of. It's the bigger amount. Usually when we're thinking of solutions, it's the liquid. Typically, we're thinking of liquid solutions. The solute is the minority component or any of the minority components, anything that's not the solvent, something that's dissolved in the solvent. We've got a smaller amount of this, and this is usually a solid when we're thinking of solutions. Like if you put a little bit of salt into some warm water to gargle or to rinse your nose or to do other things with, that solid, that salt, is our solute. That's the minority component. There's less of the salt than there is water. In a solid liquid solution, like salt in water, in a solid liquid solution like salt water, the liquid is usually considered and called the solvent, even if it's not technically the solvent. You could have more of the solid or the other thing than you have of the liquid. Solvent just generally refers to the liquid in the solution. The most common solutions are aqueous solutions. The aqueous here meaning that it's water as the solvent. Other solvents can be used, especially if we're forming solutions with nonpolar solutes, since like dissolves like. If you want to dissolve something that's nonpolar, like oils and fats and greases, you might use hexanes or other things that are similar to gasoline to dissolve them. Speaking of like dissolves like, so different solvents are often needed in different situations. Polar solutions are made of polar solvents, polar liquids, with polar solids dissolved into them. So this would be like salt water. Nonpolar solvents dissolve nonpolar solutes. So things like fats and oils and greases and stuff would dissolve into nonpolar solvents. Some common polar solvents are things like water, acetone, methyl alcohol, ethyl alcohol, that's the one you can drink. And then common nonpolar solvents, things like hexane, diethyl ether, toluene, and other such stinky and carcinogenic compounds. The way that dissolution works, dissolving things, is that we've got competition. So here we're looking at salt and water. So we've got our solvent, which is the water. We've got two water molecules, and we've also got our solute, the salt. Together, the sodium and the chloride are what we call salt. In order for the salt to dissolve in the water, this interaction, the interaction between the water and the sodium and the water and the chloride, has to be stronger than the interaction between the water and the interaction between the sodium and the chloride. If the sodium and the chloride like each other a lot, then the water will not be able to pull them apart. The sodium and the chloride will be inseparable. And that happens sometimes. Not with sodium chloride, but it happens with other compounds. So if the solvent-solute interaction are stronger, it dissolves. In the case of mixing things like water, and if these were oil instead, the oil has a strong affinity for itself. The water has a strong affinity for itself, stronger than the interaction between the two, and so they will just keep to themselves. They don't bother interacting. Not all ionic compounds are going to be soluble in water, so things like calcium carbonate. In calcium carbonate, the calcium and the carbonate ions have a very strong affinity for each other, and so they stick together rather than being pulled apart by the water molecules. When it does dissolve, like this little salt crystal here, when it does dissolve, what happens is water molecules come and they latch on. You can probably find short videos of this. The water molecules will come and latch on. They'll grab onto the sodium, they'll grab onto the chloride, and they will pull it apart. Piece by piece, they disassemble the sodium chloride crystal, and then the sodium ion and the chloride ions are stuck floating around with a bunch of water molecules, all like giving them their full attention. You can maybe imagine what that would be like to be a sodium or a chloride and just lots of people standing around you looking at you all the time. I've never talked about that before, it just came to my mind. And the sodium, because it's positively charged, gets the negatively charged dipole. Remember dipoles from earlier in the chapter? It gets the negatively charged dipole of the oxygen. The chloride gets the positively charged dipoles of the hydrogens. And so the positive and negative charges interact, and this is a stabilizing effect. So the sodium gets stabilized by all the water molecules around it. The chloride also gets stabilized by all the water molecules around it. We usually omit drawing in all of the little water molecules because it's just easier. Ions in solution are surrounded on all sides by water. We just usually omit the water part. Okay, so if we form a sodium chloride solution, you take your salt crystal, you put it into solution, and here we've omitted the water molecules for clarity. So the water is not explicitly drawn in. I don't want to get in trouble for explicit drawings. Thank you. Okay, so it's just implied that we have water in the solution. Sodium chloride dissolves, so when you add sodium chloride to water, it dissolves into sodium ions, chloride ions. There are no NaCl units. No NaCl units in the water. When it dissolves, it gets completely pulled apart. It's a different thing when it's in solution versus when it's out of solution as a solid sodium chloride. Substances that dissociate completely into ions are strong electrolytes. So the strong part here is referring to completely dissociates, and electrolytes referring to there being ions. The ions can conduct electricity, electrolytes conduct electricity. It completely separates, completely dissociates, and so we call it strong. So a strong electrolyte completely dissociates. This is not always the case. And this brings us to our fourth force, our fourth intermolecular force, and our last intermolecular force. So our last intermolecular force is the ion-dipole force. This is a force between what two things? An ion and a dipole. It's in the name. So ion-dipole force, like our dipole-dipole force, remember our second force? That was between two dipoles. This one, ion-dipole, is between an ion and a dipole. So the ion-dipole force occurs in mixtures of ionic compounds and polar compounds. The ionic compound provides the ion part, and the polar compounds have dipoles, provides the dipole part. So for example, when sodium chloride dissolves water, we've got all of these ion-dipole force interactions. I don't know why I'm circling all of them. Ion-dipole force. Any guesses about whether ion-dipole forces are stronger than dipole-dipole forces? What's the charge on our sodium here as an ion? 1 plus. What's the charge on our hydrogen here? Is it 1 plus? Or is it less than 1 plus? It's less than 1 plus. So dipoles, remember, are partial positive, partial negative. They're not full positive and negative. Ions get full positive and negative. So it's like if we have a really big magnet and a really small magnet. Our dipoles are small magnets. Our ions are really big magnets. So if you've got a really big magnet and a small magnet, that's going to be a stronger interactive force than 2 small magnets. I have once again failed to bring my dangerously strong magnets to demonstrate this for you. I have hurt myself with them on accident, but it's happened. Okay, and we will pick up talking about ions as conductors, which is not the same as engineers, next class.